But my question is about Euler's equation and how the book solves uh, did the equations with complex numbers.
Oh, okay.
So,
So I'm looking for where am I looking in the book? Complex
uh,
conjugate roots.
so I guess that would be page. I guess it's the last page of section 5.2, which is 217 at the bottom, just before the exercises.
Oh, I see. Okay.
So,
So we're looking essentially at
part C.
this last theorem here.
Yeah. And I was just curious because Euler's equation says it would be cosine x plus I sine x.
Mm-hmm.
They don't include the I, so I was wondering how would you get rid of that using Euler's identity to solve it
Okay.
rather than.
Yeah. So they've got these two complex conjugates, right?
Mhm.
So really, that would suggest, like, if I was thinking about part A here, which is really kind of where I'm at, I would think, okay, so if I applied part A to this directly, I should get y is c1 e to the, now I need r1, which is lambda plus I omega times x, plus c2 times e to the lambda plus I omega x. What did I screw up here?
So minus.
Good. Yep. The first one's plus, the second one's minus. Okay. And then if we do a little manipulation to this thing, so our first things first, I've got this exponent, right? So I'm going to kind of FOIL that exponent together or distribute that exponent out. So I've got C1a e to the lambda x times e to the I omega x plus C2 e to the lambda x times e to the, and this is maybe a little weird, but I'm going to write it that way as I times the quantity of minus omega x. One, do you guys believe that's valid?
Hmm.
Okay. And then I'm going to step over to kind of somewhere else in my brain, and I'm going to recall Euler's, which says that e to the I, and I need some kind of variable here that I'm not using, right? So normally I'd use x, but I'm going to put a theta in here. So
Better.
e to the I theta is what?
Uh, cosine theta plus I sine theta.
Perfect. Okay, so I'm kind of thinking this thing, and I'm gonna rewrite this just a little bit and put just an empty box in for theta. I know that you guys are solid with variable substitution, but I just want to make it completely explicitly clear what I'm doing here.
Mhm.
So I'm going to take this omega x that's in this box, that's in this exponent here, and I'm going to think about this I times some stuff, right?
Mhm.
So I'm going to feed that into Euler's, and I'm going to get that this is C1 e to the lambda x times, and here I've got a cosine of omega x plus an I sine of omega x. So that this whole piece here is this piece here. And this one is going to end up over here. You guys with me on that substitution? Okay, so in my second part here, I'm going to end up with a C2 e to the lambda x. And then in here, I've got a cosine of minus omega x plus I sine of minus omega x. guys with me on that? Okay. Now, quick question. Do you remember what to do with minus signs in trig functions?
I believe cosine is considered an even function and sine is an odd function, meaning that cosine, if there's a negative inside the argument, then it can just go away. And I believe sine can be factored out or factored.
Yeah, it can be pulled through, essentially. Yeah, that's exactly right. Cosine is an even function, and sine is odd. Okay, so now if I multiply this whole thing out, I'm going to have a c1 e to the lambda x cosine of omega x plus c1 I sine. Oops. What did I lose there?
E to the lambda x.
Good. I should have c1 e to the lambda x, and I guess I should just put the. I'm just going to put the I out front there. Cosine of omega x. Nope, not cosine.
Sine.
That one's supposed to be sine. So I did that distribution and then this one. And then in my second half here, I'm going to have a c2 e to the lambda x. And then I've got a cosine of omega x. And I have a minus I c2 e to the lambda x sine of omega x. You guys with me? Okay, now what?
Would you group your C1s and C2s together? Oh wait, you already kind of have that. No.
Yeah, so I think I really should group like terms, right?
Mm-hmm.
And I feel that like, oh, the C1s are like terms and the C2s are like terms. But I think I'm going to go with the functions being like terms.
Mm-hmm.
So I'm going to see that one and this one. You guys see that?
Mm-hmm.
I'm going to group those two together. So I'm going to have C1 plus C2 times e to the lambda x cosine of omega x. You guys on board with that?
Mm-hmm.
Okay, and then I'm going to have a plus, and I'm going to have an I here, and then I'm going to group up these two terms. So the coefficient there is a C1 minus C2. And then I've got a e to the lambda x sine of omega x. And then this is kind of the trick. This arbitrary constant here and this one here are just arbitrary constants, and they're different. So this is where we kind of get away saying, I'm going to call that shit A, and I'm going to call this shit B, and then I'm going to have A e to the lambda x cosine of omega x plus B e to the lambda x sine of omega x.
Okay, so you can just group that I into a constant.
Yeah, there's a little bit of complex analysis to fiddle, or a little bit of maybe complex arithmetic to fiddle with here to demonstrate that you can pick C1 and C2, so this works. But you can, and frankly, this isn't a course in complex analysis, so I don't really want to go there. But if you want to bug me in an office hour, I can sit down and we can hash that out with you.
Okay.
Suffice it to say that I is a number, right? And you're multiplying by some other arbitrary constant difference. That's some number. I'm going to call that thing B. I'm going to tend to assume that B is real. But that's also just an assumption. Like, there's no reason that this wouldn't work if it was complex. Does sort of fly?
Yeah.
And yeah, this is it is a little bit confusing because in the end, or at least maybe in the beginning of this, there really are supposedly three cases kind of lined out here, right? There's the case where there's two distinct real roots, there's the case where there's a repeated real root, and then there's the case where there's two distinct complex roots. But really, frankly speaking, there's only two cases here.
Mm-hmm.
There's the case where there's two roots and the case where there's one. It just so happens that if I want to look at a friggin' spring in the world, I need to rearrange the one where there's two complex roots because having those eyes in there doesn't really tell me about the world. Does that sort of follow?
Mm-hmm. Yeah, I just forgot about the basic trig rule where you can, with the negative signs.
Oh, the even odd. Yeah, that's a trick that really comes in handy. It should be noted that in building Eulers, you'll see it.
Mm-hmm.
So the reason that cosine's an even function is that it's all the even terms out of a Taylor series.
Okay.
And the reason that sine's an odd function is that it's all the odd terms. What those words really mean is that it acts like an even degree polynomial or it acts like an odd degree polynomial.
Oh, okay.
And you could prove with a little bit of work that if it's even or odd, then there's something to do with the Taylor series and the even terms and the odd terms. It's actually pretty freaking cool.
Interesting. I was wondering, like, why is it even or odd? But that's really cool. Yeah.
Yeah, it's really for a long time there was this thought that like maybe all functions are polynomials. Like, and some of them we just like have a hard time classifying, like sine and cosine.
Yeah.
It turns out that that's not really the case, but also kind of is the case. It's one of these like, well, yes, but actually no. In this case, it's kind of a well, no, but actually yes.
Yeah.
And it's even worse in the complex plane. In the case of real functions, the Taylor series, they might converge for a little while and then they get bad elsewhere. The Taylor series and the complex plane are a more robust tool. They're pretty freaking rad.
Right. I really want to take a complex analysis class. It sounds fun.
I think it's a super cool subject, but I'm a little biased. It is the only kind of calculus that it is the kind of calculus that I did, and I was like, "Oh, calculus is cool." Because yeah. Otherwise, it's like a tool to solve physics problems, which is fun, but not like not that interesting, I guess.
Ooh, don't let Anka hear you say that.
I mean, yeah, Anka and I we've had some talks about physics problems. She doesn't like the kind of physics problems I like. I like these physics problems like if you have an infinitely long fire pole that has a density of 1 kilogram per meter, what would the gravitational field induced by this object look like?
That actually sounds really fun.
she doesn't like that question because she's like, it doesn't have a center of mass, so it doesn't do things. Like, it doesn't matter. It's great.
Doesn't matter?
Yeah, it does not matter that a infinitely long fire pole does not have a center of mass. You can still figure out how the gravitational attraction works because it's just an integral.
Yeah,
I just thought you were making a pun about matter.
No, I don't make puns. They're the lowest form of humor. All right. Any more questions on this whole thing?
Mm-mm. No, I'm
No?
good.
Okay, cool.
And that was the only question I had for